Hey kids, hope you guys are doing okay. We've got about 6 sections left, actually about 5 sections left out of chapter 9 that we have to do in order to get done with the BC exam, or done with all the material, and then we'll just start reviewing. So that's kind of good news, and the test, from what I understand, is going to be a 45-minute online exam, and how they're going to do that, I have no idea, but as the more I get information, I'll pass that on to you, and hopefully we can get through this. Anyway, I hate that we have to. You guys have to learn this way, and to be honest, I don't know if I'm going to like teaching this way because I can't interact with you guys. Anyway, it is what it is. But I'll try to keep these lessons kind of short because I know you guys. Probably the last thing you want to do is listen to me drone on and on about sequences and series for hours. So without any further ado, let's light this candle. Anyways, you can tell, as you can see up here that I have on the screen, the definition of sequence is going to be a function whose domain is the set of all natural numbers. And so let's say we had this function here. If I said graph this thing, f of x is equal to x squared, the numbers that you would naturally plug in for x are going to be 0, 1, 2, 3, and not only that, you can take -1, -2, and so when you plot those points, you'll get this one, you'll get 1, 1, 2, 4, -1, 1, and 2, 4, and when you'll say, then what do you do? Well, you connect these with a smooth curve, and this is what's your function's gonna look like. But what you do when you connect these with the smooth curve is you're going to assume that all these numbers in between here and here are going to be numbers on this graph. Well, how do you know that 1/2 doesn't go up here somewhere? Well, because 1/2 squared is 1/4, and it's going to be right here. So this is what is known as a continuous function. Now, when we're dealing with sequence, traditionally the letters that they use at the beginning of the alphabet are going to be used for sequences. So we'll have a sub n is, let's go ahead and take a look at this same sequence. A sub n is equal to n squared, and a sub 1 is going to be 1 squared, which is 1. A sub 2 is equal to 2 squared, which is 4. A sub 3 is equal to 3 squared, which is 9, and so on and so forth. And then when we go to graph this thing, here's what it's going to look like. You'll have 1, 1, which is right here, this point. You'll have 2, 4, which is this point. So there's just going to be these points here, this point, and you don't connect it with a smooth curve because the only numbers that you're plugging in here are the natural numbers. All right, now let's go ahead and take a look at when it's in this form here, it's what is known as explicit formula. And so we can have an explicit formula as, let's look at this thing. Let's say we had 3n minus 2, and we'll call this a sub n. And so a sub 1 is going to be 3 times 1 minus 2, which is going to be 1. A sub 2 is going to be 3 times 2 minus 2, which is 4. And hopefully you guys kind of get the idea what's going on. So let's take a look at a few examples of some sequences. And the first sequence we're going to look at is this one. Let's say we have a sub n is equal to 1 minus 1 over n. So if we take a sub 1, we'll get 1 minus 1, which is 0. A sub 2, you'll have 1 minus a half, which is a half. A sub 3 is 1 minus a third, which is 2/3. And a sub 4 is equal to 1 minus a fourth, which is 3/4, and we go on and on and on and on if we want. But what I want to do, instead of graphing this on an XY coordinate plane, let's graph this on a number line. So if we were to graph this on a number line, here's a sub 1 and a sub 2. Whoops, a sub 2 is right here, which is a half. Out here is 1. A sub 3 is going to be 2/3. Here's a sub 3, and a sub 4 is going to be 3/4, and we can go on and on and on and on, get closer and closer. But what we want to do is we want to find out what the limit of this sequence is. And the way we're going to write that is we're going to say, what is the limit as n approaches infinity of 1 minus 1 over n? And as n gets bigger and bigger and bigger, this is going to blow up to infinity, and 1 divided by infinity, if you recall that a constant divided by infinity is 0, so this is going to approach the number 1. So this sequence right here is approaching the number 1. So let's take a look at another sequence here. Let's take a look at this one right here. Let's have b sub n is equal to negative 1 to the n plus 1 over n. So if we have b sub 1, let's find out what b sub 1 is. It's going to be negative 1 to the first plus 1 over 1, and that is going to be 0. So if we were to plot this thing at b sub 1, or b sub 1 is going to be 0 right here. Let's find out what b sub 2 is. So you have negative 1 squared plus 1 half, and negative 1 squared, that's going to be 1 plus 1 half, that's going to be 3 halves. So this is 1, out here is 3 halves. So we're right here, and this is b sub 2. Well, let's see what b sub 3 is going to equal to. It's going to be negative 1 to the third plus 1/3. That's going to be a negative 1 plus 1/3, which is a negative 2/3. So here is a negative 1, negative 2/3 is right here. So here's b sub 3. And if we do a couple more, let's do b sub 4. It's negative 1 to the fourth plus 1/4. And that's negative 1 to the fourth is 1 plus 1/4 is 5/4, and 5/4 is going to be about right here. There's b sub 4, and b sub 5 is going to be negative 1 to the fifth plus 1/5, and that's going to be negative 1 plus 1/5 is, that's going to be 4/5, negative 4/5, I do believe. Yeah. So here it's negative 4/5. And so what's happening is, notice, depending on whether n is odd or even, is you're going to bounce back in between negative 1 and positive 1. So if we want to take the limit as n approaches infinity of b sub n of this thing, which is the limit as n approaches infinity of negative 1 to the nth plus 1 over n, this thing is doesn't exist, because it's either a positive 1 or negative 1 depending on what this is, what that n value is. Alrighty? Okay. Alright, and that gets us to a pretty important formula here, a pretty important theorem that we need to know, and that's this. It says if you take the limit as n approaches infinity of f of x and it equals to L, then the limit as n approaches infinity of f of n is also equal to L. And you know, that may seem kind of strange, but it kind of makes sense. And let's go ahead and take a look at an example here. Let's take a look at the limit as n approaches infinity of 3n squared over 2n squared plus 5n plus 7. Well, these problems are exactly like the Bobo Botan eats DC thing. Remember that? The eats DC. But you're going to say, well, that's not a function. Well, it kind of is, but it's going to be a subset of the function. If I gave you this problem, what's the limit as x approaches infinity of 3x squared over 2x squared plus 5x plus 7? You'd say, well, it's going to be 3 halves. Well, this one's going to be the exact same thing. It's going to be 3 halves also. The only difference is the only numbers that we're going to plug in for this n are going to be natural numbers, and here you're just going to be plugging in real numbers. But when you're going out to infinity, it really doesn't matter. It's going to be the same thing. So if we said this one, what is the limit as n approaches infinity of, let's say, n squared over e to the nth power? Well, notice that you have a polynomial, and here you have an exponential function. This exponential function is always going to outrun that polynomial, and so this is going to go to 0. All right. Okay. Now, so the homework, I'm pretty much through with this section, and the homework on these are going to be pretty simple. The first thing I'm going to ask you to do is, well, let's go ahead and take a look at a couple of the homework problems here. Let's say they say a sub n is equal to 3n plus 2 over n plus 1. The first thing they're going to ask you to do is write out the first 4 terms, or first 5 terms, excuse me. So you're going to have to find out what a sub 1 is, a sub 2, a sub 3, a sub 4, and a sub 5. And then you're going to have to take the limit as n approaches infinity of this function, 3n plus 2 over n plus 1. So when we do the Bobo-Bot-Needs DC thing, the exponents are the same, so this thing's going to equal to 3. And let's kind of verify that. The bigger these numbers get, the closer and closer this thing's going to get to 3. So if you take 1 and plug in here, you have 3 times 1 plus 2 over 1 plus 1, so you'll get 5 over 2. If you take 2 and plug in there, you get 3 times 2 plus 2 over 2 plus 1. You'll get 6 to 8 over 3. And if you take 3 and plug in there, you get 3 times 3 plus 2 over 3 plus 2. So that's going to be 4, and this will be 11 over 4. And then you can go on, but you can see that this number is getting closer and closer to 3 as that number gets bigger and as this n value gets bigger and bigger. So that's what the first part of the homeworks are going to be like. You're just going to have to plug numbers in, and you're going to have to kind of see what they approach. Take the limit as n approaches infinity. The next type of problems that they're going to have is they're a little more challenging in the fact that they're going to give you this business, and you're going to have to come up with what the explicit formula is. So let's say we had this problem right here. 1 over, let's see. I got to get my glasses, kids. I can't see. Okay, so I'm back. I found my glasses. So let's say we have 1 over 2 squared, comma, 2 over 2 cubed, comma, 3 over 2 to the 4th, comma, 4 over 2 to the 5th, so on and so forth. And we want to come up with the explicit formula. And you can label it anything you want, and I'm going to just label it a sub n is equal to, now notice you have 1, 2, 3, 4, so that's going to be our n, over, and then you have 2 to the 2nd, so that's going to be 2, and you're going to start off with 2, so it's just not going to be n, because the first number that you have to plug in here is 1. So if you take 1 and plug in here, I want 2 squared, but what I'm going to have to do is just add 1 to this exponent here. So this is what our explicit formula is going to be. Alright, and that's basically it for this particular section. And oh my goodness, it's 14 minutes. I hope you guys didn't fall asleep or anything. But anyway, I'll screenshot a picture of some of the homework problems that I want you to try to do. And as far as the homework is concerned, the ones I wanted you to try to attempt are section 9.1. Let's try to do 1 through 29, the odd problems. Alrighty, and I'll screenshot those to you. Alright. Hope you guys are doing good. I'll talk to you later. Bye.